cancel each other. So today in 8.3, we're going to see what happens if the torque is not equals to 0. Meaning that the object is moving with angular accelerations. Okay, so now, if an object is moving, meaning that every particle inside the object is rotating as well. So we are going to calculate the torque by each particle. Okay, the torque from each particle. So if you look at this diagram, okay, you look at the diagrams on the left-hand side. So if you look at this diagram, now I've chosen a few points from this rigid body. Okay, so I have a rigid body here. I've selected M1, M2, M3, many points. Okay, I've marked many points in this body. So I'm going to try to calculate the torque from each of them. Okay, the torque carried by each of them. So for particle 1 and particles M2, now let's start from a particles M1. So for particle M1s, as we learned in chapter 8.1, the subtopic 8.1, the definitions for torque is equals to Fr sine theta. So based on the diagram, the force that causes the object to rotate is F1. Therefore, I substitute F with F1. And R is the radius from the rotation axis, the axis of rotations, until the points of force. So this is my R1. So I have F1, R1, and 90 degree come from the angles between F and R. So according to the diagram, it is 90 degree. So I have F1, R1 sine 90 degree. Okay. And then I'm going to replace F with MA, because that's what we have learned in chapter 4. So if you have a non-zero force, okay, a force moving with accelerations, so the reasons why I can use A here is because my force is acting along the line that is parallel to the accelerations, the linear accelerations. Remember, linear accelerations always perpendicular to radius. So in this case, I can straight away substitute F with MA. So M1, A1, R1. So where is sine 90 degree? Sine 90 degree is gone because sine 90 degree is equal to 1. So I have torque 1 equals to M1, A1, R1. And what next? Well, because I'm looking at rotationals of a rigid body, so the object is rotating. Therefore, I'm going to change the variables into the variables that can be used in rotational motions. So I'm going to replace A with R alpha. So torque 1 is equals to M1, R1 alpha 1. Okay, and then times with the R1 from previous step. And then I simplified it, I will get torque 1 equals to M1, R1 square alpha 1. And in this formula, in these answers, I'm going to call M1, R1 square as moments of inertia. Okay, so I1 is the moments of inertia of particles M1. Now, how about alpha 1? Why didn't I include alpha 1 in my moments of inertia? So, well, I will tell you soon. So let's look at the equations for M2 first. So once again, I'm going to repeat the same step for M2. So I'm using the same methods. I derive until I obtain torque 2 equals to M2 R2 square alpha 2. And again, I'm going to call M2 R2 square as moments of inertia for particle 2. Okay. Now why? Why didn't I include alpha in my moments of inertia if this is based on my derivations? If you recall what we have learned in a previous lesson, alpha for the particles in the same rigid body, they are constant. Okay, they are constant. They doesn't depend on which particles that you're using, where's the particles. Whereas M1 and R, okay, M and R, it depends on the particles chosen by you. So we have alpha 1 equals to alpha 2, and it doesn't matter which particles that you're looking at, the alpha will always be the same, which is alpha. Okay, it's constant value. So all particles have same angular accelerations, okay, because the rotating object is assumed to be rigid. So rigid means that the body won't change, the shape won't change. So they are going to rotate with the same angular velocity. They are going to rotate with the same angular acceleration. So for n amounts of particles, just now we were calculating the torque by each particles. Okay, the torque in each particles. So now you're going to look at more than one particle. So how are you going to calculate torque? So total torque is going to be equals to total mr squared times with the alpha. So like I told you just now, alpha is a fixed value. The only things that will change is the m and r. So you're going to calculate them one by one. Okay, you're going to calculate them one by one, and then you add up the torque from every single particles, and it will become your total torque in a rigid body. Okay, total torque in a rigid body is equals to summations mr squared times alpha. So this part we call it moments of inertia of a rigid body. So this I is the total moments of inertia. Okay, we're not looking at the moment of inertia for one particle anymore. Now is this the moment of inertia of a rigid body. So just now we're calculating for one particle. Now we are calculating the torque for a rigid body. Now for the rotations of a rigid body about a fixed axis, the net torque acting on a rigid body is proportional to the body's angular acceleration. That is based on our derivation just now. So we can simplify the equations, or we can rewrite the equations as summations torque equals to I alpha. Okay, and these equations actually it is analogous to the second law. Okay, Newton's second law. So summations F equals to ma. Meaning that when you compare these two equations, torque is analogous to the force, I is analogous to the mass in a linear motion, whereas alpha is analogous to the A in linear motions. Okay, so meaning that if you have another equations from a linear motions that consists of M or A, then you can replace it with I and alpha. Okay, if it consists of F, then you can replace it with torque because they are analogous to each other. Moment of inertia is defined as a sum of the products of the mass of each particles and the square of its respective distance from the rotations axis. So this is the definitions for moments of inertia. So I equals to summations m1 r1 squared. So you are going to add up the moments of inertia from every single particles. Okay, if you have one particles, you use one particles. You have two, you add up two of them. If you have three, then you add up the moments of inertia from the three particles. Okay, so I is analogous to the mass. So this is what I told you. Okay, they are analogous to each other. So if you want to use in chapter 8, you use symbol I. If you want to use it in a chapter, let's say 4, then you use M. Okay, now, just now we have a general equations. I is equals to summations mi ri squared. Okay, it depends on the moments of inertia from every particles. But it is quite impossible for us to add up the moments of inertia of every single particles inside a rigid body. Why? Because they have various shapes. So in order to calculate I for various shapes of object, we use integrations. Okay, so I is equals to integrate r squared dm. Okay, r squared dm. Well, you don't have to know how to use these equations. I'm just telling you what is the difference between the equations that we're going to look at now and the equations from the definitions. Okay, this is just for your knowledge or on reference. So now we're going to look at moments of inertia for various objects. So we have already derived the equations for you. What you have to do, you just have to apply the equations. Okay, you don't have to know how to derive it anymore by using these equations. So if you have a ring or a hoop, okay, or a cylinder, okay, with a hollow in the middle, then we use I equals to mr squared. Okay, so this is the I for this whole body, not just one particles anymore. So I for a hoop or rings or a thin cylindrical shoe it is equal to mr squared. Okay, I equals to mr squared for this shape. Now, if you have a solid cylinder, or we call this, most of the times we will apply this equation for this. Okay, if you have a solid cylinder or this, then I is equals to half mr squared. Okay, so don't ask me why this one don't have half, this one have half, because it is all based on the derivations, okay, by using these equations. So all you have to know is how to apply these two equations. And if you have a uniform rod or a thin rod with a rotations exist at the middle through the center of mass, then the I is equals to 1 over 12 ml squared. Okay, this is if you have a long thin rod shape where the center of mass is at the center. If it is at the end, then the rod. And then if you have a solid sphere means inside is solid. Okay, it's full with particles, such as the ball bearings that you have been using in your experiment. So that is what we call solid sphere. So if you have a solid sphere, the moments of inertia would be equals to 2 over 5 mr squared. Okay, 2 over 5 mr squared for solid sphere. Now, if you have a hollow sphere or a thin spherical shoes, then, okay, for example, such as ping pong. So ping pong ball inside is empty. Okay, you just have the shoes. So I is equals to 2 over 3 mr squared. So for various types of object, they are going to have a different moments of inertia. Okay, you are going to use different equations to calculate their moments of inertia. So you don't have to memorize all these equations. If you're being asked in the exam, then the equations will be given. Okay, if questions ask you to find moments of inertia, then questions will also tell you which equations to use. So you don't have to memorize it. But of course, for your assignment, you have to know how to select the right equations. Okay, you have to know how to select the right equations. Now let's look at this example. Okay, this example is not in your books. So if you want to print screen this page, you can print screen. If you want to snap the picture, you can snap. If you want to write it down, also can. It is totally up to you. Okay. So a uniform disc with mass m equals to 2.5 kg and radius r equals to 20 cm is mounted on a fixed horizontal axle. Then a block with a mass m equals to 1.2 kg hangs from the massless cord, and that is wrapped around the rims of the disc. So this is the disc, okay? Your pulley is the disc. And then you got the massless cord, okay, the massless strings, you wrap it around the rim of the disc. And then there's another object hanging right here. And after that, you let it go. Okay, you let it go, you let it drop. And questions ask you to find the accelerations of the falling object and the angular accelerations of the rings, as well as the tensions in the cord. So if you look at these questions, it is a combination of rotational motions and linear motions. Okay, you combine both rotational motions and linear motions in one question. So now let's see how are we going to solve these questions. Okay, you have two different motions, keep that in your mind, one rotational motions and one linear motions. So now we want to sketch a simple diagram for each of them first. So first of all, if you look at these questions again, there are two objects in the questions. Object 1 is the disc. Object 2 is the block. Okay, it's this block. So we are going to need two diagrams for these questions. So for the disc, okay, I sketch the disc first. Okay, now I cannot use a dot to represent the object. Okay, it is unlike in chapter 4 in the free body diagram. We can use a dot to represent the object because we assume all force acted on the center of mass. In this chapter, the force is not acting on the center of mass. Okay, it's being pulled or pushed at the edge of the disc. Okay, along the rim. So we cannot just use a dot to represent the body. Okay, because the force is being acted at a point that is not center of mass. So you just sketch the diagram of the simple diagram. Then you draw the force acting on the disc. So based on this diagram, you have only one force. You have only one force acting on the disc. The force that causes the object to rotate is the tensions. There's no other force. You don't put weight in the first diagram, in this diagram. Why? Because weight is located at the center of mass, and it doesn't cause the object to rotate. The only force that causes the object to rotate is the tensions, and we know it is located at this point. This is the part that the tensions causes the object to rotate. Even though you have the cord wraps around the object, wrapped around the disc, but only this force is causing it to rotate. And then you include the directions of rotations here. Why? The directions of rotation is very important. The reason is exactly the same as what you have been doing in chapter 4. In chapter 4, when you have an object that is in equilibrium, we use right-hand side as positive, left-hand side as negative. And in chapter 4 again, when an object is moving with constant acceleration, we take the directions of accelerations as a positive direction. Now, in chapter 8, we are going to apply the same concept. When you have an object that is in equilibrium, then we take clockwise as a negative torque, anti-clockwise as positive torque. But now, if you have an object rotate with an angular acceleration, then we are going to take the directions of rotation as positive direction. So actually, this is not the directions of angular accelerations. Directions of angular acceleration is always perpendicular to the disc. I'm just putting an alpha here to help you to connect it, to link the knowledge with what you have learned in chapter 4. So by right, this one is not the directions of angular acceleration. It is just the directions of rotation. So in this case, this is rotate in the clockwise direction. So meaning that we are going to take clockwise direction as positive torque, anti-clockwise as negative torque. So now we are done with the first diagram, the disc. Next, we are going to look at what happens to this block. Now this block, if you let it drop, it's going to move in a linear motions. So in this case, we are going to draw a free body diagram for it, like what we have been doing in chapter 4. So we use a dot to represent the object. We are going to assume all force is being acted on the center of mass, and then it is being hung by a string, a cord. So it has a tensions going up, and the weight is always going down. So it is an object, definitely is going to come with a weight. So the weight is pointing downwards. Then how about accelerations? So if the object is dropping, acceleration is going down. Accelerations pointing downwards. Meaning that in this case, in this free body diagram, we are going to use downward as positive direction, whereas upward as a negative direction. So now let's see how are we going to form the equation based on these two diagrams. We are going to start from the first diagram, the rotational motions. So these move in rotational motions. So the first equations that we're going to use is the definitions for torque. So torque equals to Fr sine theta. According to the diagram, the force that causes my object to rotate is just a tension. Therefore, I'm going to substitute R with a T. And then radius R, I'm going to keep it as a capital letter R, and sine 90 degree, because the angle between radius and tension is 90 degree. So torque equals to TR sine theta. That is the first equation that we obtain based on the definitions of torque. Now the second equations that we are going to use, is the torque for a rotating object, for a non-equilibrium object. So just now we have seen summation torque equals to I alpha. So I'm just going to write it as I alpha now as my second equations. So I have two equations, equations 1 and equations 2, based on the first diagram. based on the rotational motions diagram. Okay. Next, I'm going to look at my second diagram. Okay, the free body diagram for a hanging mass for this block. So this block is moving in a linear motions, or we call translational motions. So for linear motions, if it is moving with accelerations, then we are going to apply Newton's second law. Okay, Newton's second law. Summations F equals to ma. So based on this diagram, I'm going to take A as positive direction. Okay, meaning that if I want to expand these equations, so I have to replace the left-hand side, which is the summations F, with W minus T. Okay, positive, negative. So negative tensions because it is going up. So W minus T equals to MA. And W at the same time can be written as mg minus T equals to MA. So this would be my third equations. So I have equations 1, I have equation 2, I have equations 3. So now I want to solve these three equations. Okay, I want to simplify these three equations. I want to combine these three equations together. What should I do? So try to go through the questions again. You will see that the information that you have is the R, and then you have M, you have G, okay? You don't have the information for T, you don't have A, you don't have alpha, you don't have I. So there are so many missing information. How are you going to solve it? You cannot do simultaneous equations straight away because you have too many unknown. So our job now is to try to reduce the unknown, okay? For instance, you have M and R for the disc, meaning that you can calculate its moments of inertia. So given M is equals to 2.5 kg and R is equals to 0.2 meter, I is equals to half mr squared, and it is equals to 0.05 kg m squared. So I know the unit is kg m squared because of equations. Equations say half mr squared. SI unit for m is kg, SI unit for r is meter. So kg m squared. That is the SI unit for moments of inertia. Okay, now let's consider rotational motions. Let's look at what happens to the disc first. Okay, so just now we have two equations. We have formed two equations based on the diagram. Okay, first one is torque equals to TR sine 90 degree. The second equation is torque equals to I alpha. If you notice, both of them, they are torque. Okay, both of them, both of the equations are torque. So we can use equations 1 equals to equations 2. We can remove the torque from the equations, okay, by using this relationship. So TR equals to I alpha. You don't have to write sine 90 degree anymore because it is equals to 1. So we have TR equals to I alpha, and then I'm going to rearrange the equations. So A equals to R alpha. Therefore, I have T equals to IA over R squared. So the reasons why I put these equations, okay, why I substitute alpha with A over R, again, it is because I try to reduce the unknown. Okay, I try to reduce the unknown. So if you're going to apply simultaneous equations, you can only have two unknown in your solutions, okay, in your solutions. So in these equations, I have T equals to IA over R squared. Now, you have the values for I. You also have the values for R. The things that you don't have is T and A, okay? So you have two unknowns here. Let's recall, what is the equations that you form? What is the third equations that you form based on the free body diagram? So you have mg minus T equals to MA. So you compare with equations 4 just now, you will see that both of them, they have the same unknowns, which is T and A. So now you have two equations with two unknowns, so you can do simultaneous equations. So substitute 4 into 3. Okay, mg minus IA over R squared equals to MA. So you have the values for M, small letter m, and then you have the values of G, 9.81, I is equals to 0.05 based on your calculation just now. And R is equals to 0.2. Remember, everything must be in SI unit. Once again, this M is equals to 1.2. Remember, don't use the wrong M, okay? You form equations 3 based on the hanging block. So this M is the mass of the hanging block. So you don't substitute the wrong M here. And you just calculate the A. So A equals to 4.8 meter per second square. Okay, you substitute everything into the equations and then you rearrange it. At the end, you obtain A equals to 4.8 meter per second square. So once you have A, you can calculate the rest, okay, the other two variables asked by the questions. So questions 2 ask you to calculate angular accelerations. We know that alpha is equals to A over R, capital letter R. Remember, this R is the R for the disk. So A equals to 4.8 divided by 0.2. Then you have 24 radian per second square. Okay, 24 radian per second square. And at last, you can calculate the tensions, question C. So tensions equals to IA over R square. IA over R square, you have a 0.05 times 4.8 divided by 0.2 squares. At last, you get T equals to 6 Newton. So you're done. That is the questions in 8.3, okay, that can be asked in 8.3, rotational dynamic. So usually questions in chapter 8.3, it will involve the combinations of linear motions and rotational motions. So you have to know how to link these two types of motions together, okay, especially by using this equation. So this equation actually plays a very important role in 8.3, okay, because you can use them to link the linear motions, which is the accelerations, and the angular motions, which is the angular accelerations together as one equation. You can join them as one equations.